Okay, so today we will continue how to design our steel beam. Um, Last meeting, we covered what is the meaning of plastic hinge. As I told you, if the applied load increased, the stress on the cross section will increase until reaching yielding. After you reach the yielding, no more stress, but the cross section, more area of the cross section will be yielded until you reach that the whole cross section is yielded. At this moment, you have something called plastic moment or plastic hinge. Last meeting also, we classified our cross section to be compact, non-compact, and slender. And I told you, if you select a steel cross section from these tables, your cross section will be compact. No need to check it. However, if your cross section is built up section means you created your own cross section. We have a steel beam, steel plate, with another steel plate and another steel plate welded together. This is called built up section. You need to check if this section is compact, non-compact, and slender. Last meeting also, we talked about lateral torsion and buckling, and just a reminder, the unsupported lens and supported lens of your beam. Make sure you define it correctly. And supported lens of the compression flange of your steel beam. I'm talking about the compression flange, the flange of the beam under compression. I don't care about anything else in your beam. My issue will be with the part of the beam under compression. So lateral torsion buckling will occur. This unsupported lens between this point and this point, for example, is called LB. It will be called LB. B like book. LB like book. So if you would like to reduce this unsupported lens, we can provide this bracing. So if you have this bracing, the distance between this one and the next one, the following one, this distance will be called LB. We need to make sure this lens, the distance between, or the length of the unsupported flange lens, is minimum as much as we can. Can you see here? This is the first bracing. This is the second bracing. The distance between the two bracing will be called LB, and supported lens of the compression flange of your steel beam. This parameter is very important. Keep in your mind. Keep in your mind. If you have beam, steel beam, like this one, this steel beam is supporting a concrete slab. If you have concrete slab, supported by this beam, like this, and we have mechanical connection between both of them, in this case, your unsupported lens LB, B like book, will be 0. Every single inch of your beam is supported by this rigid slab. So in this case, the unsupported lens equals 0. We don't need any bracing. We are not worrying about the unsupported lens, we don't have any issue with the lateral torsion buckling because the top flange, which is under compression, the top flange, which is under compression of this beam, is supported every single inch. So the unsupported lens LB equal 0. But if you have bracing to support, we don't have the slab, we don't have a concrete slab. If you have bracing like these repeated every 5 feet, so the LB equal 5. Repeated every 10 feet, the LB equal 10. Repeated every 20 feet, LB equal 20. If you have concrete slab, we don't have unsupported lens, LB equal 0. Do you have any question so far? Guys, do you have any question so far? We covered today LB. So far, this is a new part. LB unsupported lens of the compression flange. I'm not talking about the bottom flange. The bottom flange is under tension. I don't care about the flange or the part of the beam under tension. We don't have issue with the lateral torsion bar. To design your beam, the design philosophy is we need the value of M ultimate, which is coming from loading, dead load, live load, whatever, and coming from structure analysis to be smaller than or equal the design moment strengths. Design moment strengths. This value, the design moment of strength, you don't need to calculate it. It's already available in these tables. If you go back to D2L, you will find a new tables I posted last meeting on Monday, which is called design of beams. In these tables, you will find the name of the cross section, and we have a value here called phi m, or phi m plastic, whatever the name, I don't care. But the design strengths or the design moment strengths of any beam is given in this table. That makes sense? So we need to make sure that applied moment from structural analysis from loading is smaller than or equal the design moment strength. I forget to mention, yes, the design moment strength is given in the table directly in only one case. If LB is smaller than or equal LP. B like book, P like pen. Oh, okay, one moment. I can understand the value of LB, like book. LB looks like the unsupported lens of the compression flange. Yes, I can understand this one. What you mean by LP? If you go to this table one more time, for cross-section, for example, W40 times 503, you will find here a value called LP. So for each cross-section in the table, we have a value for LP. Go ahead and make a comparison between the unsupported lens and the given value in the table. If you have this relationship satisfied, LB is smaller than or equal LP, that means your design moment strength will be the same one in the table, phi m plastic. This one is X, This one is X, whatever. Which is this one. Phi M plastic. Phi M plastic. Phi M plastic. Does that make sense? So Phi M plastic from table will be your design moment strengths and make a comparison between this value and the applied moment from the loading or structure analysis. So LB is the unbraced or unsupported length, is the length between points that are either braced against the lateral displacement of the compression flange. LP is the maximum unbraced length, and this value can be shown in the table. These values, LP is the maximum unbraced length from table, but LB from the construction, from your beam layout, is the spacing between bracing. If you have concrete slab on your beam, this concrete slab will provide support for the top flange every single inch. So the unsupported length or unbraced length equals 0, LB. We have another case. If you have the unsupported length, LB is greater than LP and smaller than or equal LR. If you open your table, we have another value called LR. Assume the first case is not satisfied. We have another case. The unsupported or unbraced length is between LP and LR. LP and LR from the table. Each cross section in your table have these two values. So assume your unbraced length LB, be like the book, is in between. That means your design moment strength equal this equation. We don't have a ready value for your design moment strength. We have to use this equation to figure out the design moment strength. Let me do this example and see how to design your beam, or how to make sure the applied moment from structure analysis is smaller than or equal the design strength of your beam. If this equation is satisfied, we can say yes, safe. Yes, this beam can support these loads. So we have a beam W16 time 31. So the beam is given W16 time 31. And the type of steel is given A992 steel. This beam supports a reinforced concrete floor slab. Oh, this information is very important. Do you know why? Because if your beam supporting reinforced concrete floor slab, that means we are in this case. We have a beam supporting reinforced concrete slab. That means your unbraced length of the compression flange will be 0. Otherwise, maybe in a different question, you will find the bracing and the spacing between these bracing. So you can say LB equals this spacing. But in this case, your beam is supporting concrete slab. That means that the top flange, which is under compression, is supported every single inch. So LB equals 0. And this concrete floor slab provides continuous lateral support of the compression flange. The surface dead load equal The surface life load equal, we have dead load and we have life load. We need to make sure, do you think this beam can support these loads safely? The question is, does this beam have adequate moment strength to support these loads? To answer this question, we have two parts we need to cover. The first part is the part of structure analysis. Structure analysis. What is the value of dead load? What is the value of life load? What is the value of W ultimate? What is the value of M ultimate? This is called structure analysis. Then the second step is the step of design. We need to make sure finally, we need to make sure finally your ultimate moment, M ultimate, is smaller than or equal the design moment strength. Anybody can tell me what is the value of dead load? Is it 450 or something else? We have given dead load value 450 pounds per foot. So it's ready, dead load for you. It's ready. Do you think I'm gonna use 450 only or something else? I need to listen to you. Any suggestion? Is it 450 only? Or we need to add something else? If we need to add something else, how much? Thank you, Mitchell. How much? Yes, it's the weight of the steel beam. The weight of this steel beam. Thank you. Thank you. Yes. Thank you, China. Yes. This dead load is coming from the concrete slab. As I told you last meeting or last week, each beam is supporting from center line to center line. So the value of dead load on the slab time this width is already given 450. But we need to add the weight of this beam, steel beam itself, which is 31. Do you remember the meaning of this name? The second number represented the weight of the beam for every 1 feet. So the value of dead load will be 450 plus 31. The value will be 481 pound per foot. For life load, I'm gonna use the given value 550 pound per foot. That's fine. The value of W ultimate 1.2 dead plus 1.6 life. So your value will be 1.2 times 481 plus 1.6 times 550. I got here 1,457.2. I do recommend, this is pound per foot. I do recommend to convert this one to kib. It will be approximately 5 kib per foot. I divide it by 1,000. So the value of the M ultimate, since you have simply supported beam, and under the effect of distributed load, your moment will be a parabola. The highest value of this parabola will be W L square divide 8. So your value will be W L square divide 8. W equal 1.5, L equal 30 feet. I can figure out the value of M ultimate, which is coming from structure analysis. 1.5 times 30 square divide 8, I got 168.75 kb foot. The unit will be kb foot. This is the first step or the first part of your problem, which is related to structure analysis, loading and structure analysis. Second step, do you think we are in this case or this case? LB equals 0. The unbraced length of the compression flange of your beam equals 0 because it's supported by concrete slab. I'm talking, guys, to be more specific. If I'm saying supported by, I don't mean the beam is supported by the slab. I didn't mean this, but I mean the top flange of your beam is supported by the concrete slab laterally. I mean laterally, because the steel beam is already carrying your slab. The beam itself carrying your slab. But if I'm saying your slab is supporting your beam, I mean supporting the top flange laterally. Lateral torsion buckling, against lateral torsion buckling. Okay, this is my intention. Let's go back. Okay, what is the value of LP? What is the value of LR? To make sure your LB is smaller than or in between. I think it will be smaller than LP, but make sure what is the value of LB and LR. Okay, I will open my table with this name, 16 by 31. So I will open the table for W 16 by 31. Do you think we have it? 16. Can you see 16? I have here 16 by 100. Let's see, 16 by 31 looks like we are very close. 16. Here you go. We have 16 by 31. This is the cross section. For this cross section, from this table, I can say the value of LP equal 4.13 feet. And the value of LR equal 11.8 feet. So I can make a comparison. LB is smaller than or equal LP, or LB is in between LP and LR. I think we are in the first case because the value of LB, which equals 0, is smaller than the value of LP, which equals 4.13. That means the design moment strength equal phi M plastic, which is coming from the table. From this table with the same cross section, we have this value phi M plastic, which equal 203, ready for you. 203 kb foot. Are you sure it's a kb foot? Let's go back. Your value is kb foot. 203 kb foot. So here is the applied moment from structure analysis. Here is the design moment strength. I think M ultimate is smaller than or equal, I'm sorry, it's smaller than, not equal, smaller than phi mn, that means the answer is yes. Because the question is, does this beam have adequate moment strength to support the applied load? The answer, yes. The beam is adequate, or the beam has adequate moment strength to support the applied. Keep in your mind, if this relationship is not satisfied, that means we will be in this case. That means your design strength must be done using this equation. We have another example here. But so far, do you have any question regarding this one? It's very easy. Not like the concrete beam we covered last semester, because everything is given in these tables. For steel structure design, everything are given in tables. Do you have any question regarding this example? Second example. We have a beam 14 by 68, W14 by 68 from this steel type. And it's a given. This beam has embraced supported length 20 feet with CB equal 1, whatever. So this beam, just to translate the given information, this beam is supported by bracing at this point, and another bracing at this point, and another bracing at this point, like this. And the spacing between this bracing equal 20 feet. So this is the part which is called and brace the length of your compression flange. So this is the value of LB. This is the value which was 0 in the previous example. It's not given, but we learn, or we can understand from the given information, because we have reinforced concrete slab. But in this case, the end braced length is given 20. And the cross section is given 14 by 68. Guys, the requirement in this problem, we need to figure out what is the design strength. Phi MN. Flexural strength means the design moment strength. Flexural, this name flexural means moment. Flexural mean moment. Flexural strength mean moment, design moment strength. Phi MN. So the cross section is given. Based on this cross section, I can figure out the value of LP and the value of LR. I'm gonna open my tables for 14 by 68. 14 by 68. 14, 14, 14. Yes, here you go. We have here 14 by 68. Here is the cross section. You must find your cross section. In this cross section, I can say here is the value of LP 8.69. feet. Here is the value of LR 29.3 feet. Do you think LP is smaller than or equal LP, or LP is greater than LP and smaller than or equal LR? Which case we are in? I think we are in this case. because LB equal 20. This 20 is greater than 8.69 and smaller than 29.3. So your design moment strength or flexural strength equal to this equation. CB time phi M plastic minus phi PF time LB minus LP. So CB time phi M plastic minus phi BF time LP minus LB. That's right. This one is M. This is the equation for your flexural strength or design moment strength. You will be surprised because everything is given. Are you sure? CB is a constant. We are going to use it like 1. If you would like to figure out what is the value of CB, we have a table here can tell you what is the value of CB based on what type of load do you have. If you have uniform distributed load, this is the value. If you have uniform distributed load and your beam is supported at the mid span, this is the value. If your beam is uniform distributed and supported at each third of the span, we have different value of CB. So this table can give you what is the value of CB, or you can assume it like 1. In this example, it's given 1. Phi M plastic, this cross section has a value for phi M plastic. Your value is given for phi M plastic 431. So this value is 431. What is the value of phi BF? For the same table, we have a value here for phi BF, which is given by 7.81. Oh my goodness, everything is given in the table for this cross section. 7.81 is the value for phi BF. How much? 7.81. So this value is 7.81. What is the value of LP from the table? It's given 8.69. What is the value of unpressed length? LP is given in the problem 20. I think I have a mistake here. We need to change this equation to be LP minus LP, or we can change this to plus. This one is plus, not minus. I'm sorry. Because this term must be subtracted. This term must be subtracted from this term. So we have two options. We can change this minus to plus and keep LP minus LP, or we can switch both of them. Anyway, so go ahead and use your calculator. Uh, 431 plus, that's fine, 7.81 time 8.69 minus 20 time 1, your value will be 342.6. Looks like I have a mistake in these calculations. One moment. 7.81 time 8.69 minus 20. Yes. Plus 431. Yes, very good. Hip foot. This is called the design moment strength or flexural strength of your beam. If you have information for M ultimate based on the dead load and the live load, you can make a comparison and make sure your M ultimate is smaller than or equal phi MN. That makes sense? That makes sense. We have another example. But so far, do you have any question? So guys, make sure this equation is written correctly. This equation can be CB. Sorry. Can be CB time phi M plastic minus phi BF, but LP minus LB. This one is correct. Or CB time phi M plastic plus phi BF time LB minus LB. Just to make sure, I need this part to be subtracted from this one. That makes sense? So yeah, this one is okay, this one is okay. We have another example. We have another example. Yeah, just a moment, guys, just a moment. For this example, we have single story steel frame. The connection between columns and the beam may be assumed to be simple shear connection. So this beam can be assumed simply supported. We have a support here and we have a support here. This beam BC can be considered simply supported beam under the effect of this distributed load. The loads are factored load, so this value of load 8 kb per foot can be considered W ultimate. So we don't need to figure out how much dead load, how much live load, how much 1.2 dead, 1.6 live, everything is given. So I can say the bending moment on this beam is a parabola. The highest value of this parabola in ultimate equal W L square divided. Your W is given, you are lucky, 8 kb per foot. Your span is given 30 feet square, divide 8, so your moment will be 900. Kb foot. That makes sense? That makes sense? The floor supported by the beam BC does not provide any intermediate lateral support to the beam. We don't have any intermediate lateral support. This information can say your arm brace, the length of the compression flange of your beam will be 30 feet. Do you agree? This beam is supporting a slab or floor, whatever, but the floor does not provide any intermediate lateral support. So we don't have any lateral support between this column and this column. So the unbraced length of your beam is the whole length, which equals 30 feet. This is a type of steel, and we need to select W shape. So this is a design problem. The applied load is given, which is a part of structural analysis. And we need to start the part of the design. Since the cross section is not given, we need to assume one. We need to assume cross section. What do you think? I can assume W shape. You need to open your table and select this cross section. Which one? Do you think this one will be good? This one will be good? Oh my goodness, we have many. So which one I'm gonna start with? Any suggestion? I have many cross section until here. So which one I'm gonna start? What do you think? I'm gonna start with the highest one. I cannot say it's wrong, but it's not economic. Probably the highest one or the biggest one, it's very big to be used, and it will be more expensive. So any suggestion? I have suggestion. The applied moment equal 900 kPa doesn't make sense for me to select this one. Does not make sense for me to select this one. Does not make sense for me to select this one. Anybody can tell me why? Does not make sense for me to select any in this page, to be clear. Anybody can tell me why? The applied moment on the beam due to the given load is 900 kPa. So I said I will not use any in this page or in this table for this page. Do you know why? Keep in your mind your design strength of your beam. We have two options or two cases. The first case, your design strength directly equal phi m plastic, or in this case, the design strength equal phi m plastic minus something. This part will be subtracted from phi m plastic. That means your design strength can be phi m plastic or something less than this value. We don't have a third option. We have only two options. Your design strengths, like this example, equal phi m plastic directly. For this example, which is the second case, m plastic is reduced by something to give you the final m design strength, which is less than the phi m plastic. This is from the table. That makes sense? So if you look to these cross section in this table, in this page, here is the value of phi m plastic. You will find all of them is smaller than 900, which is the applied moment. Doesn't make sense to select one of them, because if you select one of them, your beam will be unsafe. That makes sense? That makes sense? What do you think? Did you get it? Yes or no? Okay, so to be smart, don't select a cross section at the beginning. Your design strength is less than 900. You are kidding. You are wasting your time. So I need to go up. Probably this one will be good, 1400. Probably this one will be good, 1100. Probably this one will be good, 1000. That's fine. because we need something greater than 900. Maybe, I'm not sure, but maybe this one will be good. Because keep in your mind, we can be in this case. So your design moment strength is not the same M plastic. It will be reduced a little bit. That makes sense? So 915, I'm not sure 100%, but maybe. Especially your LB and LR, I think LB equal 30 is greater than LR, so this value will be reduced a little, maybe more, not a little. So I don't recommend also this one. So to be sure 100%, we can select this one. Let's try this one. 30W 30 by 99. So I'm gonna assume my cross section is W30 by 99. For this cross section, 30 by 99, here is the value of LP, here is the value of LR. 7.42. I'm sorry, LP 7.42, LR equal 21.3. I think you are in this case, LB, which is 30, is greater than LP and smaller than. No. We have LP greater than LR. I'm sorry, this one will not work. This one also will not work. We need to select a cross section to satisfy the value of LP 30. So we need to go up. Do you think we can do it? Yeah. Unfortunately, we need to go up more to make sure the given value for LR is greater than the value of LB, which is 30. Do you think we can select any here? Yes, this one can work. Probably this one. Maybe this one also. Maybe yeah, this one also can work. So we can select a cross section with LR greater than 30 to make sure your LB is greater than LP and smaller than LR at the same time. So we need to select a cross section with LR greater than 30 at least. So let's try this one. W27 times 161. W26 or 27, 161. 27 times 121. The value of LP, the value of LR. How much? So LP 11.4, the value of LR 34.7. That means LB is greater than LP and smaller than LR. It's not economic solution because the 30 feet is unsupported, which is not good. I highly recommend it to provide any intermediate support to make LB equal 15. This is my recommendation, but this is not the case in this problem. That's fine. So your phi MN equal CB time phi M plastic minus phi BF time LB minus LP. What is the value of CB? If the value of CB is given, that's fine. We can use it 1. If the value of CB is not given, we need to go back to this table. You have distributed load and your beam is supported from the beginning, and at the end, I'm gonna use this. But if it's not given, I'm gonna use the value in the table. So the value of AM plastic for this cross section, this value equal 1930. Minus phi BF for this cross section, phi BF equal 31.3. LB equal 30, LP equal 11.4. Then I can find the design strength of this cross section, which equal 1930 minus 31.3 times 30 minus 11.4. Your value equal 1,347.8 kb/foot. That means your M ultimate is smaller than phi MN. That means your cross section that you assumed W27 times 121 will be safe and enough. Any question? Why did you not change the value? We have this option. We have this option, minus or plus. Which one is you put first, LP or LB? Does that make sense? If you put minus, so you have LP first minus LB. If you put plus, it will be LB minus LP. But the final conclusion, you will subtract this one. Keep in your mind, LB is greater than LP. So this term will give you a negative value. I'm sorry, positive value. So positive times negative, the final is negative. This one will give you a negative value. So negative times positive will be negative. That's final conclusion. I need to subtract this term. That makes sense? Yes. Thank you. It's confused a little bit, but you should understand it. We have, if you put negative, we have LP first. If it's a positive, LB first. Does that make sense? There is a big difference. But the final conclusion, I need to subtract this number from phi M plastic. Guys, that makes sense? Let's see the last example. Where is the last example? Yes, I put positive, but I put LP minus LB. In this example, I put negative, so I put LB first and LB second. Both of them works. Here you go. This one is LB first. This one is LP. This one is LP second. This one is LP. So this term will give you a negative sign. This term would give you a positive sign. So if you multiply negative sign by positive, the final is negative. If you multiply positive by negative, the final is negative. So the final answer will be the same. Okay, that's fine. No problem. Okay.